Okay, so first, let's talk about the test. Um, the scores were good. I don't have any, like, I'm not going to do number one here because, you know, people did badly on the test or anything. But I, this is one, it's pretty quick for me to go through, and it's a kind of a key thing to understand. So I'm going to go through this anyways. Um, and then I'll ask if you have any other questions after that. But on exam 3, number 1, it looked like this. There was a pin joint down here, um, and the structure looked like this. All of the joints between members were pin joints. Um, and there was a pin and slot joint here. And the angle of that, well, it didn't give an angle. It just showed that it was in an angle because all we're doing is free body diagrams, I guess. And then an 800 Newton force acting down there and a 400 Newton force acting this way. And these were numbered 1, 2, 3, 4, 5, just so we all had the same numberings. And I'm going to letter the joints too because I'm going to talk about those. So A, B, C, D, I'm going to call these. And sometimes in structures problems, you can get away without thinking too carefully about, you know, what member you're going to consider the joint to be a part of, what member you're going to consider forces to be applied to. But this is one where you really can't get away without thinking about it. And that's because individual joints have more than two members being joined. And so when you have more than two members being joined, you have to kind of have a system. What's the joint going to be a part of? What's the force going to be applied to? Really, in a way, those are the same question. Because if you think, like, for example, this 800 Newton force is being applied to that pin at B, then if the pin at B is part of member 1, then that's what that 800 Newton force is being applied to. It's being applied to that pin. Okay, so I'm going to start out. You don't have to do this. I don't do it on problems unless something's very confusing to me. But I'm going to start out by just drawing side views of all of these joints so that we can see what we're associating the joint with. So I'm going to start out with the joint A. And a side view looks like this. We have the ground connected to, so you can think of the ground, maybe I'll think of this as like a single thing. The ground and the bracket are, the bracket is just part of the ground. And then we have member 1 going up and away from us. And then we have member 2 that's just going straight away from us. And then these are all connected by a pin. Okay, and that's the only stuff going on at A. So this is member 1, this is member 2, this is the ground. And we're going to consider that pin to be part of the lowest numbered member. So all of the shaded stuff is member 1. Okay. And then I'm going to go to joint B. And this one, if we're looking at a side view, we have member 1. That's trying to get a little too fancy. Member 1 is going, if we're looking at B, member 1 is going down and towards us if we're looking from the left side. Member 3 is going down and away from us. Member 4 is just going straight away. So this is 1, 3, 4. And then we have the pin here going through them all. And then we also have the 800 Newton force applied to the pin. Okay. The lowest numbered member connected at this joint is member 1. And so that pin is going to be part of member 1. And then I'll go to C. So here we have member 2 going. So now I'm sort of picturing looking at it from the right side. It doesn't matter which side you look at, but in that case, member 2 would be going straight away from us. Member 3 would be going up and away from us. Member 5 would be going up and towards us. The pin goes through all of them. And then you can imagine the slot. I don't really know how to draw this, but so the slot connects to the member there. Okay. So this is member 2, member 3, and member 5. The lowest numbered member connected at joint C is 2. So that pin is going to be part of member 2. So all of the shaded stuff is member 2 for our purposes. Okay. I mean, you can always lump multiple members in with a body in a free body diagram. We do it all the time, you know. If you draw a free body diagram of a person's body, it includes all these cells or whatever. We're lumping all this stuff in. So you can choose, and we're just calling all of this member 2. Okay. And then D, if we're looking from the right side, we have 4 going away from us. We have 5 going down and away from us. Then we have the pin going through, and then we have the 400 Newton force applied to the pin. This is member 4. This is member 5. The pin is part of the lowest numbered member. Thanks. And so all of this is part of member 4. Okay, so now we have this stuff. We can reference this when we draw the free body diagrams. Okay, so free body diagram of member 1. All of these have a weight, 10 kilograms. The mass is 10 kilograms, so the weight is 98.1 newtons. But then really the key stuff is what's happening at the joints. So down at the lower left, that's the joint A. Let's think about, this is member 1. What's touching member 1? So if member 1 is the shaded thing, all the shaded stuff. So it's touching the ground, And it's also touching member 2. So over here, I'm going to write this as like our RA. That's the force applied by the ground. And we also have the force on 1 by 2. And that's everything. You can see that from the side view. So now we can go to the joint B. Again, we're looking at member 1. This is a free body diagram of member 1. It's touching members 3 and member 4. And it also has the 800 Newton force acting on it. So I'll draw the 800 here. And then the force vectors are the force on 1 by 3 and the force on 1 by 4. Okay. Anybody have any questions about the thought process here, how I'm using those side views to figure out? And like I said, you don't have to draw those side views, but sometimes if you get confused, it can help you get unconfused, you know. All right, so now let's go to member 2. So this is the horizontal one. We have the weight force in the middle. Over at the joint A. Okay, so look at A and what is touching member 2. The only thing touching member 2 is the shaded stuff, the pin. The ground is not touching member 2. So we're not going to have any kind of reaction from the ground here. We're only going to have a force on 2 by 1. And that's a force by a pin joint, so it's an unknown, you know, a full unknown force vector. I could write that as F21, but eventually, in order to solve this, you'd have to remember that this is the negative of F12. But this is the key thing here. There's no reaction from the ground. And you can figure that out by looking at that side view. Okay. And if you put that reaction in from the ground, your answers are going to be wrong. Then we'll go to the joint C. What's touching member 2? Member 2 here is the shaded region. So we have contact with 3 and contact with 5 and contact from that slot. Okay. So this is going to be force on 2 by 3, a force on 2 by 5, and then the pin and slot joint is going to be, force is going to be perpendicular to the slot. And I can just call that RC. Be careful, this is a scalar variable because we know the direction. So this variable should not have a vector symbol on it. This is just a single number that we're trying to find. Now, free body diagram of member 3. We have the weight. And then up at the top, that's joint B. So let's look at joint B and see what 3 is touching. 3 is touching 1, the shaded stuff, but it's not touching 4. And it's not touching that 800 Newton force. Okay? So there's not going to be any F34. There's not going to be any 800 Newton force. There's only going to be F31 or negative F13. And then at joint C, 3 is touching 2, but nothing else. It's not touching the slot and it's not touching 5. So here we have negative, no, this is the first time we've F2. Let's see. Oh yeah, that's going to be negative F23. Okay. And again, if you put an RC in there, or you put a F35 in there, that's going to give you the wrong answers when you do your calculation. Then we'll go to member 4. 98.1. Over at the left side, that's joint B. 4 is only touching 1. So here we have negative F14. And then at joint D, it's touching 5, and the 400 is applied to it. So we have the 400 going this way, and we have F45. And then last is the free body diagram of 5. At joint C at the lower left, 5 is only touching 2. So we have negative F25. And then up here at the joint D, 5 is only touching 4. The 400 isn't applied to it. So we have negative F45. And one thing that you can sort of look at to sort of generally just kind of check your answers for, kind of a sanity check. As the numbers go up, you're going to have fewer forces applied to these things, because the higher the number is, the less likely it is to be the lower numbered member at any joint. So if you're still having, 3 forces applied at joints when you get to your highest numbered member, you probably thought about something wrong. And again, I'm not grading you based on these side view things, but if you ever kind of get confused about what's happening in a joint, thinking about that side view can help you get it straight. Any questions about that? Okay. Anybody want to talk about anything else on exam 3? Okay. Any questions about any of the homework assignments in the last week that you'd like me to go over? Can you go over number 7? Sure. In internal loads? Yeah. Okay. Okay, so there's number 7. And always when you're doing internal load calculations, you're coming up with piecewise functions for that internal tension, that internal shear force, and that internal bending moment. And the places where those piecewise functions change are places where they're point loads, so point forces or point couples, or places where distributed load functions change. In this case, this has a mass of 30 kilograms. I think that might be the issue, that you have a distributed load here, and I assigned this before I gave you the stuff on distributed loads. Okay, well, let me go through how to approach this. So when you do internal loads, weight is always going to be a distributed load. And it's always going to be a uniform distributed load. And the magnitude, so with distributed loads, there's always this key defining function Q of x. And what this Q of x does is, for a given x, Q is the magnitude of the distributed load at that x value. Okay. The first step in any internal loads problem is calculating the external loads. It turns out that if your external loads that you don't know are all on the far right side of the beam, you can skip that step because that'll never come into your calculations. If you don't want to, it doesn't hurt anything to calculate those external loads. They usually come in handy in a problem in some way or other. But we can do the internal loads here without ever calculating the loads applied by the wall. Okay, just only because it's at the far right of the beam. So I guess I'm going to skip that step for now. And I'm going to draw a free body diagram of what we know going into the internal loads calculation. Okay, so over here, this fixed joint, there's going to be some reaction, and there's going to be some reaction couple. That's just the stuff that that fixed joints, the loads that fixed joints apply. We don't know what those are, but it turns out it doesn't affect the problem. Then there's going to be a point couple over here. That has a magnitude of 600 Newton meters. And a point force of 500 newtons. And then at the midpoint, there's 1,000 Newton force going to the left. I'm going to draw it underneath just for clutter because I'm going to draw the distributed load on top. Okay, and as long as we've been doing rigid bodies, we haven't been doing internal loads yet. We've been treating whole bodies as a rigid body. We've treated weight forces as point forces acting at the center of mass. But that's not really what weight does. Weight really applies a little bit of force to every little bit on the body. And so what the weight really is a uniform distributed load where the magnitude of that distributed load is the same everywhere along the member. And the magnitude is the total weight force, which would be 294.3 newtons, divided by the length of the member. In this case, the length of the member is 1 meter. So this is 294.3 newtons divided by 1 meter, or 294.3 newtons per meter. Okay. And the distributed load function, you can think of like that function Q. We can represent it with a single function for the whole thing. Over the whole beam, Q as a function of x is just a constant function, 294.3. Okay, that's because since this thing is uniform, at this x value, what's the magnitude of that distributed load? 294.3. At this x value, what's that distributed load? 294.3. It's constant. Okay, so it's easy to find that function. Now we have to identify where we're going to have to, how many cuts are we going to have to do? So notice that the subfunctions of these these piecewise internal loads, okay, can only change at the middle, because the middle is the only place, this is where the subfunctions can change. Oh, I didn't write it down. But the subfunctions can change at point loads or where that Q function changes. The Q function doesn't change, so all we have between the endpoints is at the midpoint we have this point force. Okay. I mean, there are point loads here too, and there are point loads here, but those are at the endpoints. Like, we're already starting at the starting endpoint and ending at the ending endpoint, so that doesn't change anything. Okay, so we're going to do one cut that looks like that's going to start over here. Hold on. Okay, we're going to do one cut that looks something like this. It starts at the left end, and it goes to somewhere before that point force. That's going to be our first cut. So, okay, I'm going to say cut 1 is for x values between 0 and 0.5. And I'm just going to draw a representative piece that goes from all the way at the left end point to x, where this x could be anything between 0 and 0.5. And I'm going to put in the loads that we have on this piece. We have the 500 Newton force. We have the couple. We haven't made it to the 1,000 Newton force yet. And we have the distributed load. And then we have the internal loads, which is it's just the fixed joint loads applied to the left piece by the adjacent material. Okay. Now that we've chosen a piece to isolate, we can represent that distributed load as a point force. This is an equipolant system. Remember, equipolant systems only are relevant when you're talking about rigid bodies. Okay, so before we chose what to represent as a rigid body, we couldn't make this switch. But now that we've chosen our piece that, has a length of x, we can redraw this. And we have the 500 here. We have the 600. We have the point force representing the weight, and then we have the internal loads. Okay, so how do we figure out what this point force representing the weight is? Well, let's think about that rectangle, the shape of that distributed load. Okay, the length of it, you can see, is x. The height of it is, we figured out that this was 294.3. A rectangle has its centroid right in the middle, so that's where we're going to apply it. And the magnitude is going to be the area of this rectangular shape, so 294.3 times x. Okay, that's the area of a rectangle. And so this is 294.3x. And since it's right in the middle, we know that this is x over 2, and this is x over 2. And now we can write out Newton's laws. If you want to, this is a rigid body. You can write out the table. It always works for rigid bodies, and use that, calculate the cross product to get the moments, and it'll work perfectly fine. For horizontal things, you can save a little time. I mean, saving time isn't the greatest thing, most important thing in the world, but you can save a little time by just recognizing that horizontal forces don't produce a moment. Vertical forces produce a moment that's equal to the distance along the beam times the thing, and then you just have to figure out whether it would produce a clockwise or a counterclockwise rotation. So let me do this both ways. So let me write it out as, so rho, force, moment. And I'm going to always, for these internal loads, put my about point here. You're always free to put your about point anywhere you want in statics, and you are here too. But if you ever have a minute, try putting your about point somewhere else, and you'll just see the math gets messier. So it's always in your interest to put your about point over here on the left end. Okay. Okay, so the 500 Newton force, rho vector is 0. Force vector is 500, 0. Moment is 0. Then we have the couple of 600. For couples, we don't care about these. That's a counterclockwise moment, so it's positive. Then we have the 294.3x. The rho vector is x over 2 0. The force is 0, negative 294.3 x. So the cross product is negative 147.15 x squared. Then we have t. The row vector is x, 0. The force vector is t, 0. Cross product is 0. You can see there that was a horizontal force, and that's why it produced no moment in the end. Then we have V, the shear force. The row vector is x0. The force is 0, negative V. Cross product is negative Vx. And then last is the couple M. For a couple, we don't care about these, and we just add this on as M. So now I'm going to do it the other way, and we'll see that this all matches. Okay, so for Newton's second law, we have a force vector 500, 0. (600) is a couple, so that doesn't appear in Newton's second law. Then we have a downward force of 294.3. Times x. Then we have a force to the right of t. And a downward force of v. Those are all the forces, and those add up to zeros. And so if you solve those, you get that t is equal to negative 500, and v is equal to negative 294.3 x. And then we'll go to the moment equation. Again, we're always going to have our about point at the left end. Okay, so the 500 is horizontal and it goes through the about point, so that doesn't produce a moment. The 600 we're just going to add on because that's a couple. The 294.3, I'm going to start out by saying plus or minus. And the distance to this is x over 2. And the force is a magnitude of 294.3x. And now for the plus or minus, we just have to think, if this is the hinge that it can rotate around, would this force make the body rotate clockwise or counterclockwise? So what do you think here, clockwise or counterclockwise for that downward force? Clockwise, and so we're going to take the negative. Clockwise is always negative. Then we go to t. That's horizontal, so there's no moment. Then we have plus or minus a moment arm of x times a force of v would that downward force V make it rotate clockwise or counterclockwise? Clockwise. So this is negative again. Then we'll add on our M. And if you compare this to the equation you would get from the table, they match. Okay. So once you get used to doing it this way, it's quicker for these horizontal beams. You know, the table is still very useful for things that aren't horizontal beams, but in this case, you can save a little time. Again, like, it's not time that you're going to need on tests or anything like that. So if you feel more comfortable writing out the table, you can always write out the table for any rigid body. Okay. If we solve this, we get M is equal to, so 147.15 x squared plus Vx minus 600. I'm just doing the algebra now. And then we can substitute in our what we got for V into this V. So M is equal to 147.15 x squared minus 294.3 x times another x. So this is x squared minus 600. And so M is equal to negative 147.15 x squared minus 600. Now we can do our derivative checks that'll sometimes help you find mistakes that you've made. It won't find every mistake, but some of them. So, okay, we know, so here are our checks. The first one is dm dx needs to be equal to V. So if you take the derivative with respect to x, you get negative 294.3x. So those match. Then the second one says negative dv dx has to be equal to q. dv dx is 294.3. Negative dv dx is positive 294.3. That matches our function q. And so this one works. And so we don't have any reason from that to doubt our answers. Any questions about that first cut? Okay, well, we need two cuts because we have this point force acting in the middle. So our second cut is going to go from the left end to some arbitrary point after that point force. So there's going to be our second cut. All right. So cut 2 is for x values starting at 0.5 and going to 1. So our piece looks something like this. So we have the 500. We have the couple of 600 Newton meters. We have the force of 1,000 newtons. We have the distributed load representing the weight. And then we have our internal loads that are applied to our isolated piece by the adjacent material. And this distributed load still has a height of 294.3 newtons per meter. Okay, let's figure out some of these distances. So this distance is 0.5 meters. And the distance all the way to the end is x. One thing that gets confusing about this to people, or sometimes it'll be clear and then suddenly like at 11:30 at night you'll get confused about it, is that x value says it's from 0.5 to 1. But notice that the piece doesn't start at x equals 0.5. The piece we're isolating always starts all the way over here at the left. Okay, that x only refers to acceptable values for where the right end is. Okay, so this x is only referring to where the right end is. The left end is all the way, always all the way at the left end of the beam. Okay, otherwise we'd have to have internal loads at the left end too, and it would be chaos, Okay, well, before we can do the calculations, we have to represent that distributed load as a point force. So again, it's going to be just the same as it was before because it's uniform, but let's think through that again. So we have a rectangle with a length of x and a height of 294.3. The centroid of a rectangle is right in the middle. And since the weight is acting straight down, we don't care anything about we don't care at all about the height of that centroid. We only care about the left to right location. And then the area come on. The area of this rectangle is 294.3 times x. That's just the length times the height, So now I can redraw this free body. We have the 500. We have the couple. We have the 1,000. We have the weight acting at the midpoint, and that's 294.3x. And then we have the internal loads. And the key distances here, this distance is x over 2. This distance is 0.5. And this distance is x. Okay, you can write out the table if you want. It'll give you perfect answers. I'm going to do it like this. Newton's second law says 500, 0. Newton's second law doesn't care about moments produced by couples, so I'm leaving that off. 0, negative 294.3x plus negative 1000, 0 plus t, 0 plus 0, negative v is equal to zeros. M is a couple, so that doesn't appear in Newton's second law. And so T is equal to positive 500. V is equal to negative 294.3 x. And then I'll go to the moment equation. My about point, like always during these cuts, is going to be at the far left. So we have the positive 600. And then we have plus or minus x over 2 times 294.3x. Is that positive or negative? The moment produced by the 294.3x. Negative because it's clockwise. This is a horizontal force, so it doesn't produce a moment. The tension is horizontal, so it doesn't produce a moment. Then we have plus or minus x times the force of V. Is that positive or negative, the moment produced by V? Negative, because that's clockwise again. That Vx always comes out negative. So you can just, you'll get used to just writing minus Vx there. Plus M is equal to 0. And so M is equal to Vx plus 147.15 x squared minus 600. Plug in the V from above, and you get M is equal to negative 147.15. I sort of did two steps there. I substituted in and then added up the two x squared terms. And now do the checks. So first, dm dx has to be equal to v. And second, negative dv dx has to be equal to q. Dm dx is negative 294.3x, which is equal to v, so that one holds. dv dx is negative 294.3. Negative dv dx is positive 294.3. That was our q value, so this one holds. And now we have our internal loads. And if you wanted to write them out in a piecewise function form, people don't normally do this, but so what's your internal tension as a function of x? You could think of it as, so from cut 1, we have that T is equal to negative 500. and that's for x's between 0 and 0.5. And then from our cut 2, we have that it's equal to positive 500 for x's from 0.5 to 1. And if you graph that, it looks like this. And then just to try to trigger math professors, engineers always draw a vertical line between those two. It doesn't make mathematical sense really for a function, you know, but it actually does kind of make practical sense because point forces are really never exactly point forces. Those are always idealizations of very narrow distributed loads. And so if this was a distributed load, you would just get a very slightly angled line that would look very much like this. V and M, in this case, in this problem, those are not piecewise functions. In general, they will be. So our V is just equal to negative 294.3 x which would look like this. So it would start out at 0, and then at x equals 1, it would be here. And it's just a linear function like that. And then for the bending moment, we had negative 147.15 x squared minus 600 so we started out at negative 600. When x is equal to 1, we ended up at negative, add those two together, negative 747.15. This is concave down. And so it's going to look something like this. It's a quadratic shaped function that's concave down. I'm not, on exams, I'm not going to make you graph these out or anything like that. But you can imagine how it's helpful to visualize what's going on by graphing these out. You can just use Desmos or something for that. What do these internal loads tell you? So these internal loads are the first indication we have about where material is likely to break. We haven't been able to calculate anything like that up to this point. And when you take deformable body mechanics, or most universities call it mechanics of materials, the whole class is going to be devoted to kind of calculations of how likely something is to break, to stretch, that kind of thing. So, okay, is there anywhere along the beam where the internal tension magnitude is bigger or smaller. Not really. You can see that it's smaller just along the midline, but everywhere else the magnitude is the same. When you have a positive value of internal tension, that means it's in tension, it's being stretched. When you have a negative value, that means it's in compression, it's being smushed. Okay. What about the shear force? Is there anywhere where we're more concerned about this thing breaking due to shear force? Yeah, we're not concerned at all at the left end point, and we're getting more and more concerned as we get closer to the wall. Okay. And then what about the bending moment? Well, it tells kind of a similar story to the shear force. We're not, well, it still has the possibility of breaking due to bending at the left end, but it gets worse as you move towards the wall. And so the overall story here is, remember, let's look back at the original shape. If you have a beam like this that's loaded this way, you're most concerned about this beam breaking as you get close to that connection with the wall. Okay, and that's useful information to know. You might then bulk up the material or something as you get closer to the wall. You know, there are design decisions you could make so that that would be less of a problem. Any questions about that one? Okay, let's do another example that's similar to that, but this time I'm going to give you time to go through the steps. And then, depending on how much time we have left, maybe I'll just go through one with a non-uniform distributed load. But okay, let's start with this one. So let's say that we have a beam that it's connected to the floor with a pin joint on the right end. It's supposed to be straight. I just wiggled it by accident. And then we have a roller on the left side. And let's say we have a 200 Newton force at the center. Let's not do that. Just to make this go a little quicker. Let's just say it's this, and the whole length is 2 meters. And let's say that the mass is 20 kilograms. Calculate the internal loads in the beam. All right. In the last one we did, we had a fixed joint with the wall on the right end. It turned out we didn't have to calculate those external loads. Generally, you do have to calculate the external loads before you start. And in this case, you have to. And the reason you have to is because there's this unknown load from the roller that we need in order to do the cuts. Okay, so take a couple minutes and calculate the external loads here. I mean, this is just a very simple rigid body problem, and you're going to calculate the reaction load at the roller and the reaction load at the pin joint. Go ahead and do that. Feel free to talk to each other as you go, ask me questions as you go. But I'm just going to let you go through stuff, then I'm going to go through it, and you can kind of spot if you make mistakes on any of these steps. Okay. So free body diagram of the whole thing. the mass is 20 kilograms, so that's 196.2 newtons down. Then we have this unknown, we'll call this N, and then we have an unknown force vector over here that I'll call R. And I said that you should always put your about point at the left end when you're doing the cuts. When you're doing the external loads, it's not helpful in the same way. So you can, but you don't have to. So I'm going to put my about point over here at R. So Newton's second law says 0n plus 0 negative 196.2 plus Rx Ry is equal to 0. And so, and then moment equation says negative 2n plus 1 times 196.2 is equal to 0. So n is equal to 98.1, and R is equal to 0, 98.1. And so if I draw the full free body diagram, we have 98.1 here, 98.1 here, and then the weight is really a distributed load, uniform distributed load. That's equal to 196.2 divided by 2 meters, so 98.1 newtons per meter. Okay, so that's sort of our starting point. How many cuts do we need to make for this body? Just one. Yep. There are no points between the endpoints where there are point forces or point couples, or where the distributed load function changes. Okay. Over the whole thing, our distributed load is defined by this Q is equal to 98.1 newtons per meter. I'll leave the units off here. So one cut. And so this cut has to be relevant for the whole beam. So our cut 1 is going to be for X anywhere between 0 and 2 meters. Okay, so take a few minutes and see if you can work through the process of doing that cut, calculating the internal loads, and then I'll go through it. And if you make any mistakes, this will help you pinpoint, where you thought about something the wrong way. So our cut is going to be something, this is just a general representation of some X value between 0 and 2. So start out with a piece like this. There's the 98.1 Newton force there. There's the distributed load of 98.1 newtons per meter there. And then there's the internal loads applied by the adjacent material. To do the calculation, we have to represent that distributed load as a point force. This distance is x. And so if you look at this rectangle, it has a length of x, a height of 98.1. The centroid is in the middle, and the area is 98.1x. And so I'll redraw this free body diagram, replacing that distributed load with an equipolant point force. So we have 98.1 there. We have a downward force at the middle of 98.1x. Then we have the internal loads, T, V, and M. Newton's second law says 0, 98.1 plus 0, negative 98.1x plus, I'll put the T and the V forces into a single vector, so that's T in the positive x, V in the negative y. And you get that the internal tension is 0, and the internal shear force is negative 98.1x plus 98.1. And now I'll use the moment equation with that as my about point. That 98.1 is at the midpoint, so the moment arm is x over 2, and that would produce, with this as the hinge, that would produce a clockwise moment. So we have negative 98.1x times x over 2 plus m minus vx is equal to 0. So m is equal to vx plus 49.05 x squared. Substitute in the v from above, and you get that m is equal to 98.1 x times another x, so x squared, plus 98.1 x plus 49.05 x squared. And so m is equal to negative 49.05 x squared plus 98.1 x. Now do the checks. The first one says dm dx has to be equal to v. And the second one says negative dv dx has to be equal to q. dm dx is equal to negative 98.1x plus 98.1. And that's equal to v. So that one holds. So far, so good. dv dx is negative 98.1. Negative dv dx is positive 98.1. And that was our q. So that one holds. Any questions about that? Okay, so let me do another example. So this time I'm going to do a distributed load that's not uniform. So let's say we have a pin joint at the left and a roller at the right. And we'll apply a force of 1,000 newtons that way. And this time we have a distributed load that's shaped like a triangle. And the magnitude of this is 2,000 newtons per meter at its highest point. And let's say that this is 3 meters long. And we'll neglect the weight on this. Okay, so we want to calculate the internal loads here. What's the first step we have to take? So first we have to calculate the external loads unless they happen to all be at the right end point, because then they wouldn't come up in the cuts. So to calculate the external loads, we have to isolate the whole thing. It's just a statics problem. We have an unknown force vector over here. I'll call that RA because that's a pin joint. We have a roller over here, RB. We have 1,000 Newton force here. And then we'll represent, now that we've chosen the body to represent as a rigid body, we can replace that distributed load with an equipolant point force. So that is going to be 2,000 times 3 divided by 2. So that's going to be 3,000. And the distance is this is going to be 2/3 of the length, so this is 2 meters. This is 1/3 of the length, so this is 1 meter. And I'll put my about point over here for this calculation. Newton's second law. Like always, you can write out the table, no problem. Just takes a few seconds. But I'm gonna use the sort of shortened approach. So we have RAX, RAY plus 0, negative 3,000 plus 1,000, 0 plus 0 RB is equal to zeros. And then the moment equation, we have negative 2 times 3,000 plus 3 times RB is equal to 0. So RB is equal to 2,000 newtons, and RA the vector is equal to negative 1,000 for x, and then 1,000 positive for y. And now I'm going to draw, this is kind of an extra step, but I think it's an extra step that can help avoid mistakes a lot of times. So I'm going to draw out the full free body diagram with everything we know. So we have, I guess I'll draw these out in their directions. We have RA over here that's 1,000 that way and 1,000 up. And then over here we have 1,000 to the right and 2,000 up. And then we have our distributed load like this with a maximum of 2,000 newtons per meter. Okay, well, when you have those uniform distributed loads, calculating your Q function is easy. In this case, you have to think about it a little. We're going to use the equation for a line for that Q function. So our Q of x is going to be mx plus b. You can see that it's a linear function. And the first thing we need to think about is what that y-intercept is. So when x is equal to 0, what is the magnitude of that distributed load? 0, so we can get rid of that. And then for m, we can just think about the rise over run. So it starts out at a height of 0 and rises to a height of 2,000 over a distance of 3 meters. So this is 666.6 repeating as a slope. And so our Q function is 666.6 repeating. I'll leave the units off, but that's the function that describes the height. For any x value, plug in the x value, and that'll give you the magnitude of that distributed load. Okay. Now, how many cuts do we have to make for this? Are there any? Yeah, just one. There are no point forces or point couples, and there's no places where that Q function changes. And so we just need one cut, and it's going to represent the whole thing. So it's going to represent anything, any x value from 0 to 3. And so I'm going to just make an arbitrary cut. Come back. Okay, so I'm going to just make some arbitrary cut like this. Okay. So here is my cut. We have a 1,000 Newton force that way and a 1,000 Newton force this way. When I drew that cut, it didn't include the right endpoint, so we're not going to have that 2,000 and that 1,000. we are going to have the internal loads that are applied to the included piece of material by the excluded material. And then we're going to have this distributed load. But there's one little complexity here. In our original piece, we know that at a maximum, this gets to a height of 2,000 newtons per meter. That's not true anymore because this is an arbitrary piece that's cut off somewhere in the middle. It doesn't get all the way to that 2,000. Okay, this length isn't 3 meters anymore, it's just X. So what's the height of this triangle when you get out here to this value X? Yeah, perfect. That's what that Q function tells us. Okay. So, whoops, Q of X, I forgot to put in the X here. You know, that's the linear function. I just forgot to write the X on my equation. So the height, when you get out here to a value X, is 666.6 repeating times X. Okay. Now we can do all the same stuff we did before. It's just the algebra is going to get a little bit uglier. So our triangle, you know, we're trying to find the area and the centroid. Our centroid is going to be here, where this is 2x over 3, and this is x over 3. The height of our triangle is 666.6 repeating x, and the width is x. And so what's the area of that triangle? Base times height over 2. So this is 666.6 repeating x, the height, times the base, divided by 2. And so we have 333.3 repeating x squared. And now I can redraw this. We have the 1,000 and the 1,000 up. We have the internal loads. And then we have the point force of 333.3 repeating x squared. Okay, and as far as the key distances, the distance from the left end to that downward force representing the distributed load is 2x over 3. And the distance to the right end is x. And now it's just like before. Newton's second law says negative 1,000, positive 1,000, plus 0, negative 333.3 repeating x squared, plus t negative v is equal to zeros. So t is equal to positive 1,000, meaning this member is in tension, not compression. And v is equal to negative 333.3 repeating x squared plus 1,000. And now we'll go to calculating the bending moment. You might have this thought at some point as you're doing these calculations. Wait, one of our checks says that always for any x value, dm dx has to be equal to the shear force, which is the same thing as saying m is equal to the integral with respect to x of the shear force. We have a shear force function here. Why not just integrate that with respect to x? Hey, yep, that's exactly right. So that's a perfectly valid way to do it, but you'll have to deal with the constant of integration. And it's not a horrible thing to deal with, but it sort of makes it, it tends to make it not that much easier than just going through this way. And then the result is that you have an answer that you don't have a way to check. So to me, it's just better to keep going through Newton's laws, use the moment equation, and then you have that derivative thing as a check at the end, you know. But if you want to do that integral, it's a perfectly valid way to do it. Okay, so moment equation. So these two don't produce a moment. The two on the left end. We have a clockwise moment with a moment arm of 2x over 3. Clockwise means negative, and a force of 333.3 repeating x squared. Then we have plus m minus vx is equal to 0. So m is equal to vx plus, this comes out to be 111.1 repeating x cubed. So m is equal to negative 333.3 repeating x cubed plus 1,000x plus 111.1 repeating x cubed. And so the final answer is m is equal to negative 222.2 repeating x cubed plus 1,000x. And now do your checks. Okay, so dm dx is negative 666.6 repeating x squared plus 1,000. Something went wrong. 2x over 3. So, I mean, here's the kind of thing that check can help you catch. So this should be, I just calculated this wrong. This should be 222.2 repeating x cubed. And so this should be 222.2 repeating. And then when you do that subtraction, this comes out to be 111.1 repeating x cubed. And now when you take that derivative, you get negative 333 x squared plus 1,000, and that's equal to v. So now that works. See the benefit of doing that check. You know, you can catch some dumb little mistakes. And then dv dx is negative 666 x. Negative dv dx is positive 666 x, which is our q function. And so both of those checks work. Any questions about that? Okay. One thing about the test on Thursday, this is as much as the test is going to cover. I am going to give you an assignment to do some friction stuff, but that's not going to be on the test. So as you're preparing, just focus on this. But there is going to be one more daily assignment for you to do. Well, you should go back and like think through all of the assignments up to this point because it's cumulative. But yeah, it's going to be kind of slanted towards the most recent stuff. So I would say it's going to be heavy on structures and trusses and internal loads. Yes?
Is this exam any longer?
Nope, just 2 hours. Yeah.
If we use the generalized method to solve the truss formulas, are we going to lose points?
The general? Oh, no, not at all. You can always use the general method. Yeah. Max, do you have a question?
The exact same question.
Oh, okay, great. Yeah, I mean, I'm very pro the general method, you know. I think a lot of times, like, engineering classes make you feel like the key to everything is speed, you know. But I've never been in an engineering job where the difference between getting the right answer in an hour and getting the right answer in 3 hours made any difference at all, you know. So do what you know is right. Is going to give you the right answer. That's my philosophy. Okay, that's all.